I'm ready.
Great, very good. Okay, so I think we can go. We're also streaming live on YouTube, so I guess we can go live now. And let us begin. So again, once again, a very good morning, good afternoon, and good evening. Once again, depending on whatever part of the world we're logging in from today. These are difficult times, and I would say thank God for science to at least provide us with a modicum of sanity. So we are so delighted to have Professor Renu Malhotra as a distinguished speaker as part of the Mysteries of the Universe Institute Lecture Series 2, the second installment, hosted by the Indian Institute of Technology, Roorkee in India. Professor Malhotra is a planetary scientist and the Lewis Foucault Marshall Science Research Professor and the Regents Professor of Planetary Sciences at the University of Arizona. She works on solar system physics, including the orbital and thermal evolution of small bodies, Pluto and the Kuiper Belt, planet formation and early solar system evolution, resonance and chaos, and other planetary systems with related interests in nonlinear dynamics. As we know, the asteroid 6698 Malhotra was named after her on December 14th, 1997 by the MPC, which is a minor planet center. She's also credited by the MPC with the co-discovery of a trans-Neptunian object in the Kuiper Belt. And I guess what would be of particular interest, especially to the IITians today in the audience, is that Professor Malhotra did her master's in physics from IIT Delhi. Her awards and honors include, she was awarded the Harold C. Urey Prize in 1997, the Outstanding Alumnus Award from the Indian Institute of Technology, Delhi in 2006. She was elected the Galileo Circle Fellow at the University of Arizona in 2010. She was elected to the American Academy of Arts and Sciences and the National Academy of Sciences in 2015. She became the Lewis Foucault Marshall Science Research Professor and the Regents Professor at the University of Arizona in 2016. So with that brief introduction, I would request Professor Malhotra to please deliver your lecture. Professor Malhotra, please.
Thank you very much. Can you hear me?
Loud and clear.
Great, okay. Thank you, I'm pleased to be here. I understand that this is a lecture series that you're doing on the mysteries of the universe. And what I'm going to talk about is the solar system. It's our immediate universe, if you like, our immediate neighborhood in the universe. And what I'm going to tell you is that the solar system has not always looked like it does now at its ripe old age of the number that you see on your screen. It's easy to remember, 4.567 gigayears. It's astonishing to me. It's always been, when I learned about this, how precisely we know the age of the solar system. And later on, if you want, you can ask me about how do we know this and what does it actually mean. And so what you're going to hear today is that about 4.5 gigayears ago, near the birth of the solar system, or towards the end of the birth of the solar system, the orbits of the planets were more compact. There was a lot more debris, what we call debris in planetary science, that is to say small bodies, asteroids, comets, planetesimals, we call them. About 3.9 gigayears ago, this debris cleared up. Mostly, we have only small traces of it left now, and the planets settled into their present orbits as we know them today. And it's rather a fragile arrangement of planets that allows us to actually exist and be talking here. So I hope you'll get a sense of the way the solar system came about, or what we've learned about it in the last few decades. I thought I'd say a little bit about myself, and this is what I have to say very quickly. So I live in Tucson, Arizona. Arizona is the place where you see these giant saguaros. It's the southwest desert region of the United States, and as Dr. Mishra already told you about my career and so on, what I'm interested in is the architecture of planetary systems. And I think of the architecture as how the planetary masses and orbits are arranged. And it's no accident. It doesn't come about by accident. There's physics and chemistry and very, very complex dynamics that goes into arranging planetary systems. And I'm interested in how they form and they change over time. So this is probably the oldest topic in physics. It goes back goes back to, well, the start of physics, if you like, is Isaac Newton, who discovered the law of gravity. So understanding orbits, understanding what happens to planetary orbits over long times is, I would say, the first, the most, the oldest topic in physics. And it consists of physics and astronomy and mathematics, and it's at the intersection of these disciplines. My own migrations, if you like, were, I was born in New Delhi. I lived most of my life in Hyderabad. And then I went to IIT Delhi for my undergraduate studies, which led to a master's. At the time, it was a 5-year master's degree. And then I went, so there's IIT Delhi. It's an iconic building with this amazing architecture. And that was back in 1978. That's a picture of me right around when I went to, when I was an undergraduate starting at IIT. Then I went to, after IIT, I went to Cornell University, where I earned my PhD in 1988. I stayed there for a postdoc for a year. And then I had a postdoc, then I lived in many places in the United States. Cornell was in upstate New York. Then I went for a postdoc to Caltech in California. And then I worked in Houston and Illinois. And for the last 20 years or so, I've been in Tucson, Arizona. So it's a little funny for me to think that this is the place where I've lived most of my life, in Tucson. I've lived in very many places. I've been a migratory person practically all my life. This is a picture of me, my husband, and my 2 daughters. Let's see, go on. So my studies were physics practically throughout, and as an undergrad, graduate student. And then when I was a graduate student, I discovered this area of dynamical systems and chaos theory, which was in its heyday when I was a graduate student. And from that, I migrated to this area known as planetary dynamics. And now it's its own discipline of planetary science. It has evolved even in the last 20 years. This discipline has evolved from being more physics oriented to more space exploration and even more geosciences now, as we get to planets, visit planets, and understand them like we understand Earth itself. So on to this, my lecture, the meat of this lecture. So since most of you probably don't think about the solar system every day, here's a place to put yourself in context here. So the solar system is here's the sun, the large planets, and this is I like to think of it as, there are 4 or 5 distinct neighborhoods in the solar system. There's the inner solar system, the outer solar system. So the inner being mostly interior to the orbit of Jupiter. And then Jupiter outwards, I think of that as the outer solar system. So on this scale, you don't even see most of the inner solar system. So we are approximately there in the terrestrial planet region, the inner planets, the rocky planets, followed by going outward from the sun, the asteroid belt. And then going beyond Neptune is the Kuiper belt. And I picked up, I highlighted one object in the Kuiper belt known as Pluto, which used to be known as a planet, but is now considered a dwarf planet and a member of the Kuiper belt. And then the whole solar system is surrounded by the Oort cloud at very large distances, roughly a third to half the distance to the nearest stars. And one thing that will show up quite prominently in this lecture is all the small bodies in the solar system. So the two main reservoirs of small bodies are the asteroid belt and the Kuiper belt. But there are also these stragglers in between. So for example, around the Earth, near the Earth and the terrestrial planets, there's a whole slew of small bodies called near-Earth asteroids or near-Earth objects. And then in between the giant planets, Jupiter through Neptune, there are these, so I call them stragglers. These are unstable. These are not stable reservoirs like the asteroid belt and the Kuiper belt. Instead, these are objects that are on very unstable, chaotic orbits. And they have lifetimes, dynamical lifetimes that last much shorter than the age of the solar system, typically millions or on the order of 10 million years, as opposed to billions of years. Around, something, when I got into this business, Pluto was the 9th planet. This is what we knew about the solar system. The major planets were in this common plane, mostly circular or nearly circular orbits in a common plane, whereas Pluto, the 9th planet, did not fit in. Its orbit was much more elliptical, and it's highly tilted, as you can see in this picture. Pluto is it's literally and figuratively eccentric. Its orbital path overlaps that of Neptune, which you see on the sketch on the right, which is from the top view. So there's Neptune's orbit, which is practically circular. It has an ellipticity of about 1%. So it's out of round by about 1%. Pluto, on the other hand, is out of round by 25%. Oops, let me, okay. And then it's also tilted to so if you do a side view, which is on the left, it's tilted to the plane of the planets by something like 15 to 17 degrees, which is huge. The scale of the orbital plane offsets amongst the major planets is on the order of 1 to 2 degrees, whereas Pluto is off of that plane by some 15 to 17 degrees. However, although its orbit intersects, you could say, Neptune's orbit, it is not in danger of crashing with Neptune. And the reason for that is it's in an orbital resonance with Neptune. And that we can see the geometry and the physics of that orbital resonance in this little animation that I'll show you in a moment. It's best seen in a rotating frame. So, so think about being on a carousel at a fair, and the carousel is rotating at a frequency, at an angular velocity equal to Neptune's mean angular velocity around the sun. So that's our rotating frame. And in that frame, you'll see, and I'll hit the start button in a moment. Oh, there we go. You'll see that Neptune, so the sun is at the center. Neptune is doing a tiny little oval because its orbit is 1% out of round. So its angular velocity changes by a little bit. So here we are in a frame that's going at a constant angular velocity equal to Neptune's mean angular velocity. And in that frame, you see that Pluto makes this Lissajous-like figure. So first of all, you'll see that it's going retrograde. It's going in the clockwise direction, whereas the planets revolve around the sun in the counterclockwise direction. The reason for this retrograde in this rotating frame is that Pluto's angular velocity is, on average, smaller than Neptune's because it's farther away. Its orbit is bigger than Neptune's. So by Kepler's laws, its angular velocity is lower. So when you go into this rotating frame, the average motion is in the opposite direction. And then the other thing you see is these loops that Pluto makes. These are the perihelion loops. When it comes closest to the sun, and when its orbit distance is actually smaller than Neptune's, you see that its longitude is away from the instantaneous longitude of Neptune. So its perihelion always occurs on average around 90 degrees away from Neptune, and that location oscillates with a period of some 20,000 years around this plus minus 90 degree location. And what this is, so there are two perihelion loops that you see, and that's because the ratio of the mean angular velocity of Pluto to Neptune is in a ratio of 2 to 3. Or in other words, Neptune, for every 3 orbits of Neptune, Pluto makes 2 orbits, two revolutions around the sun. So this is known as a 3 to 2 resonance or 2 to 3 resonance. The terminology is not very settled. So this peculiar orbit, it's very delicately arranged. So in phase space, there's a very tiny volume where this kind of oscillation can happen, this kind of libration. It's known as a libration in celestial mechanics. And so the question, the big question when I started in planetary science, one of the big questions was, how did Pluto, what was this peculiar orbit of Pluto, how did it come about? And some years later, after I'd been mulling this, I came up with an answer, which was published in a couple of papers. And the answer I came up with was that we could understand Pluto's orbit and its properties if Neptune had not formed where we see it today, in the orbit that we see it in today. That if Neptune had formed closer to the sun and had migrated out to its present orbit, then one could show that an object, a small object, a dwarf planet like Pluto, which would have initially formed in a normal orbit, circular, coplanar with the planets, and not in a resonance, just a generic orbit, not in this very special part of the phase space. If Neptune had migrated outward, it would have captured Pluto in this resonant orbit in a kind of mode locking behavior that some of you who are physics students might be familiar with the mode locking phenomenon. That this mode locking would have happened, and Pluto would have been pushed into this more elliptical orbit and more inclined. Its inclination would have been kicked up resonantly. And I have a cheesy little animation here that I made with Keynote. So you see Neptune migrating out. As Neptune migrates out, the locations of its resonances, outward resonances, in other words, where the distances from the sun, where the orbital period is in these small integer ratios, those locations would have migrated out. And any object like Pluto, which formed nowhere near the resonance, when the resonance caught up with it, it would have gotten trapped in that resonance and then moved along that resonant orbit. And in the process, also, so this was the hypothesis that I made. And there was a prediction for this hypothesis. The prediction was that any small bodies, any population of small bodies, if they existed beyond Neptune, would show pileups in these resonant orbits. And so this is, in other words, the skyscraper-like skyline that you see there would be the prediction that the orbits of small bodies beyond Neptune should be piled up at these resonant locations. Not only that, there were other parts of this prediction that in those resonances, the orbits would be eccentric and inclined. But before I get to showing you some more on that, let's ask the question, what would make Neptune migrate? This seems like a pretty weird thing to propose, that Neptune wasn't formed where it is today. What would have made it migrate? And the answer is that when in the early solar system, as I mentioned to you before, in the current state, we have a small amount of small bodies in the solar system. But in the ancient solar system, the number of small bodies, the population, their masses would have been much larger. And over time, that population was cleared up through the gravitational perturbations of the planets themselves. So these small bodies were scattered and ejected through the gravitational interactions with the planets. And this is a cartoon that shows that. So the ancient solar system, more than 4 gigayears ago, with lots of debris. And then the solar system today with nearly cleared up space in between the planets. And the only places where the debris remains, or traces of the original debris remains is beyond Neptune and interior to Jupiter. Okay, so we have the asteroid belt that we've known for a long time. And in the last 20-ish years, we've also discovered the Kuiper belt beyond Neptune. How does this migration happen? So those planetesimals, that debris that interacts with the planets and then gets cleared up, has a back reaction on the planets. It's not just that the planets, they eject or clear up, scatter and eject these small bodies and clear up the space in the solar system. They also have a back reaction on the planets. And this cartoon movie, it shows you the principle of that. What you'll see is a cartoon solar system, which is the sun, Jupiter, and Neptune, and a planetesimal, a small body, an or Kuiper belt object in this case, that comes by, has a close encounter with Neptune, gets its orbit changed, then has another close encounter with Jupiter, has another orbit change, and you'll see that there's a back reaction on each of those planets. Okay, so what you saw is as this small body had a close encounter, Neptune kicked it inward, and it then had a close encounter with Jupiter, which kicked it outward. Okay, so this specific sequence, what this does is that Neptune's orbit gets a tiny bit bigger. It's of course exaggerated here. Any individual small body won't do such a big change. So Neptune's orbit gets a little bit bigger because it tossed this small body inward and gained orbital energy, and the orbit got bigger. And Jupiter tossed this object out into a hyperbolic orbit and lost orbital energy to this object. So this object carried away some orbital energy, and Jupiter's orbit shrank a tiny bit. Now, this is the average effect, it turns out, of what trillions and trillions of planetesimals that would interact with the planets and clear out the solar system. This would be their average effect. It's a statistical phenomenon. So as the objects interact with Neptune, some of them will be tossed inward, some will be tossed outward. The ones that are tossed inward will typically have this kind of final fate that Jupiter, because there are other planets inward of Neptune, the other planets will keep tossing these objects inward until they hit Jupiter. And Jupiter, being a very massive planet, has such a big kick that it tosses these objects into hyperbolic orbits. The net effect, because the outer planets, Neptune and Uranus and Saturn, are less massive than Jupiter, their average effect is to transport these small bodies from outside to inside until this Jupiter barrier, and Jupiter tosses everything out because it's such a massive planet. And so consequently, the back reaction on the planets is that Jupiter migrates inward and Neptune migrates outward. And the other two planets, Saturn and Uranus, it's not easy to say just on the basis of reasoning out and analytical formulations. So we found the answer to what happens to the other planets through numerical simulations. And I'll show you some of that in a moment. So when I had this idea, I did some calculations, and I was able to derive that one of the things that happens is that when Pluto or Pluto-like objects get captured in a resonance, their eccentricities get kicked up as they migrate together with Neptune in that resonance. And the final eccentricity of Pluto can be linked to how much Neptune migrated. So the amount of migration of Neptune is then related to how eccentric Pluto gets. So assuming that Pluto started off in a pretty circular orbit, we can then predict or we can say how much Neptune migrated to account for Pluto's eccentricity. And what I calculated in that paper was that to account for Pluto's 25% eccentricity, Neptune must have migrated out by at least 5 astronomical units. Okay, so Neptune's orbit radius currently is 30 astronomical units. So this would be a pretty big movement, migration of, so it would have expanded its orbit from about 25 to 30 astronomical units. An astronomical unit is the distance of the Earth from the sun, the orbit radius of the Earth's orbit. Okay, so, and this is a lower bound because, of course, Pluto might have gotten captured and at some point as Neptune was migrating, so Neptune might have migrated even more before Pluto got captured in this resonance. And this was confirmed with computer simulations of this, the N-body simulations of this process or this phenomenon later on, many years later, actually. Also, since subsequent to this hypothesis being proposed, there were the Kuiper belt was discovered, and now we know something on the order of 4,000 Kuiper belt objects. And this is each dot that you see in this figure is a Kuiper belt object, and this is a selection of them because these are I selected the bigger ones of those. The smaller ones have not well-determined orbits yet. And of the well-determined orbits, this is what it looks like in this plot of semi-major axis. That's the average size of the orbit. And on the vertical axis, you see the eccentricity of the orbit, how elliptical the orbit is. And what you notice is that there are these vertical structures. These are resonances with Neptune. This is where so Neptune is at 30 astronomical units. And there are objects that are Kuiper belt objects that are locked in a 1-1 resonance with Neptune. So they have the same orbital period as Neptune, or these other resonances that are marked in prominent populations in a 4-3 resonance, the 3-2, the 2-1. And Pluto is one of those in the 3-2. The 3-2 turns out to be the biggest population of Kuiper belt objects in resonance. And then in between the 3-2 and the 2-1, you see these are mostly non-resonant objects. These are not in resonant orbits. Nowadays, they are called informally as the classical Kuiper belt. These are the ones that one would have expected as the leftovers of planetesimals in normal standard orbits at relatively low eccentricities, more or less circular orbits. But these higher eccentricities piled up in these resonances is what this hypothesis of Neptune's migration predicted. And it has been confirmed with these data now. This particular population in the 3-2 resonance is called Plutinos. It's informal names. These are not official names. Naming of small bodies is carried out by an international body known as the International Astronomical Union. And these are, so each of these objects like Pluto, for example, and other objects actually have names, and they're determined by a committee of the International Astronomical Union. Plutinos is not a name that they sanction, but it's commonly used in the literature. Okay, so when we look at this pileup in resonances, there's a better equation that relates how much Neptune migrated to the eccentricities and the inclinations of these objects, and that is this combination here. So I showed you that simple equation that I derived long ago, how to relate Pluto's eccentricity to Neptune's migration. There's an even better, more accurate way of doing that. And that is there's actually an adiabatic invariant. When an object gets captured in resonance, this combination of its orbital parameters, the semi-major axis, eccentricity, so A, E, and inclination, I, this combination is preserved. Some of you might have done the three-body problem, seen the three-body problem and the Jacobi integral at some point in your classical mechanics classes, perhaps. This is related to the Jacobi integral. It's in the three-body problem, there's one conserved quantity known as the Jacobi integral. This is not exactly the Jacobi integral, but it's related. It has to do with, it's a combination of these orbital parameters that's preserved under this migration of Neptune. So if an object gets captured in the resonance, its semi-major axis will change, its eccentricity will change, its inclination will change, but this combination will be preserved. And from that is how we can derive that Neptune must have migrated out now from these maximum eccentricities and inclinations. We can deduce that Neptune must have migrated out by at least 10 astronomical units. Okay, this is a rare thing in astronomy that we have a prediction and we can actually measure something about something that happened deep in time. This kind of the process that produced this distribution happened 4 billion years ago. Okay, so there's more physics we can bring in, and we can ask things like, so the planetesimals, as they were getting cleared out, and their back reaction on the planets produced this migration. There's angular momentum conservation principle, there's energy conservation. So the planetesimals are carrying away energy and angular momentum. And we can deduce from that the total mass of planetesimals that's needed to change Neptune's orbit by 10 astronomical units. And that turns out to be about 30 times the mass of the Earth. So the total amount of planetesimals that were scattered and ejected from the solar system, we can deduce, was on the order of 30 Earth masses. They're small bodies, but their total mass was 30 times the mass of the Earth. And then we can also deduce that because if Neptune migrated out by 10 astronomical units, how much did Jupiter migrate inward? And that answer turns out to be about half an astronomical unit, because Jupiter is, of course, much more massive. And so it needs to move only a little bit to account for this energy and angular momentum conservation. So we can deduce that Jupiter migrated inward by about half an astronomical unit. That might not seem like a lot, but we'll see that it has actually very important and very measurable, observable consequences in the inner solar system. Okay, so numerical simulations of planet migration were not possible some 20, 30 years ago when I first wrote those papers, because computers were just not big enough, powerful enough to do these n-body calculations where n is thousands, or nowadays we can do tens of thousands of particles. And but back then one could not do that. But so one of the first n-body simulations of this process was done by my postdoc, Johan. And this is a figure from that paper where all we did was we placed the outer planets. We simulated the solar system containing lots of small bodies. Our small bodies were actually not so small because, again, the n in the n body that we could do initially was actually only on the order of about 1,000. So our small bodies were as large as, I think, the mass of Mars or something like that. But nevertheless, we did this calculation of embedding the planets in a disk of planetesimals and seeing how they migrated, what happened to the whole system. So I'm not showing the small bodies here, only the orbits of the planets. On the horizontal axis is time, and the scale is 30 million years. And on the vertical axis is the semi-major axis, and you can see that Jupiter, Saturn, Uranus, and Neptune on the top left migrate a tiny bit when we have a planetesimal disk with a total mass of 10 Earth masses. And on the bottom right, when we have a very massive planetesimal disk of 200 Earth masses, the planets migrate a lot, and the migration is rather noisy because our individual planetesimals are quite large. So you can see that the tens of Earth masses is the magic number that produces a moderate amount of migration, not too little and not too large. And so these this simulation was the first one that confirmed that the planets would in fact migrate in the fashion expected from those simple arguments. And since then, there have been many other more sophisticated simulations possible. I won't go into those. Instead, I'll turn to something else, which is, are there other observational tests of this hypothesis? I told you about these resonant populations in the Kuiper belt, but what about in the inner solar system? So I'm going to tell you about two other observational consequences of this. One is how the asteroid belt is arranged. There are signatures of this migration, particularly mainly the migration of Jupiter, which has a big imprint in the inner solar system, and also something that has to do with the geosciences, impact craters on planetary surfaces. And these are going to be quite complex arguments unless you're familiar with these topics. So I'll go through them slowly enough, I hope. And I hope I'll do justice to the intellectual weight of these discoveries and understanding that has come about in planetary science in the last decades, 2-3 decades. Okay, the asteroid belt. Now, probably everybody's heard about these gaps in the asteroid belt. They're known as the Kirkwood gaps. They were discovered by Daniel Kirkwood back in the middle 1800s, when there were only about 100 asteroids that had been discovered. And what he noted was that that asteroids were missing in orbits that were resonant or in small integer ratios with the orbital period of Jupiter. Okay, so he related the locations of the gaps in the asteroid belt to these orbital resonances with Jupiter. What you see here, the figure that you see is semi-major axis on the horizontal axis. So that's the average distance from the sun. It ranges from 2 astronomical units to about 3.5. So the asteroid belt is in that range. So about twice the distance of the Earth, going to about 3.5 times the distance to the Earth. And Jupiter is at 5 astronomical units. So there's a rather gap between Jupiter and the outer edge of the asteroid belt. The inner edge is just outside of Mars orbit. Mars is at around 1.5 astronomical units. And you see these very big dips. This is all the asteroids that we know. The total count now is close to 1 million. 1 million asteroids have been discovered. And the gaps show up very prominently. But there's this is observationally biased by the smallest asteroids. The gaps are owed, now we understand that the gaps are owed to dynamical chaos. And this is a very subtle effect. It's not obvious why Jupiter's, that the frequency, the angular frequency of asteroids, which is related to small integers to Jupiter's orbital angular frequency, would produce gaps. In fact, early simulations, numerical simulations, did not find any problems with any issues, any stability issues with asteroids being at these resonances. And so that's a whole other story that we can talk about what causes these gaps. It's actually it's a very interesting story. The other thing I want to point out about those gaps is we also understand now that these are the sources of most meteorites that arrive at Earth. So when we discover meteorites on the Earth, most of them have come from the asteroid belt, and they're traced to places, these resonances in the asteroid belt. Okay, so that's all I'm going to say about that. We'll see a little bit connection to that later on. What's the effect of Jupiter's inward migration on the asteroid belt? Well, we have to look at the large asteroids, which are much less numerous. And the reason for that is that the large asteroids are less mobile. So they've been in their orbits, in their current orbits, since the time that they were placed in their current orbits. So their orbits haven't changed greatly over the last gigayears under radiation forces. Asteroids that are smaller than about 10 kilometers or so, their orbits migrate under radiation forces. And so we cannot say that, we cannot look to those smaller asteroids to say where they were 4 gigayears ago when this migration was happening. But the larger asteroids should reflect the effects of this migration. So what we looked at, this was work done with a graduate student, David Minton. We looked at the large asteroids with a diameter bigger than 50 kilometers, and there are about 1,000 of those, big enough sample to study patterns in their orbital distribution. And what you see here is their orbital distribution of these large asteroids, and the gaps are visible. These are the gaps, the Kirkwood gaps with Jupiter's in small integer ratios with Jupiter. There's another very important resonance, and it's not this resonance with an orbital period. It's known as the Nu-6 resonance. It defines the inner edge of the asteroid belt. This is actually a very long period. This resonance has to do with the precession rate of Saturn's orbit. And that precession rate is, you might think, well, shouldn't Jupiter have the bigger effect in the asteroid belt, not Saturn? And that's true. The precession rate of Saturn's orbit is forced by Jupiter. So this is indirectly related to Jupiter as well. Okay, but it is an indirect connection. But this is a very powerful resonance. And if we place an asteroid or any object in that region today, very quickly, on the order of only thousands of years, its orbit very quickly, if you put it in a circular orbit, its orbit very quickly becomes elliptical, more and more and more, to the point of eventually becoming parabolic. And it often ends up hitting the sun. They're called sun-grazing asteroids. So sometimes small asteroids under radiation forces move around and enter this region, and then their orbits become nearly parabolic, and we see them. We've observed them as sun-grazing asteroids. Now, so that was a tangential comment. So what would this distribution look like if asteroids uniformly filled the dynamically stable regions? What you see here is that this is not uniformly filled. There are these gaps, and there's also some trends, radial trends that you see that are not obvious that they should be there. The original planetesimal disk, the physics of planet formation expects that this should be almost a uniform density in some major axes, which is a slightly decreasing density in radial distance and in surface density in a disk of objects. Okay, so we did a computer simulation with initial conditions that are uniform in semi-major axes. And then we said, well, we'll see what happens, take the planets where they are today and see what kind of profile they create under planetary perturbations after 4 gigayears. And after 4 gigayears of planetary perturbations with the planets in the current configuration, this is the profile we get after 4 billion years. So the planetary perturbations produce this profile, and we can compare it to the observed belt. We see those gaps, the planets produce those gaps. They produce this profile or this emptiness near the inner edge. But there are also some differences. So the brown histogram that you see is the observed belt that I showed you before. And the white histogram is the one we find by simulating under the current configuration of the planetary orbits, the giant planets' orbits. The discrepancies that you see are marked by these magenta ovals. And in the inner asteroid belt, you see this profile that there's more depletion observed than the planets can create in their present day orbital configuration. There are all the other gaps. So everywhere outside to the anti-sunward direction of these mean motion resonances, what are known as the 3-to-1, 5-to-2, these orbital resonances with the Jupiter. On the anti-sunward side, or towards the Jupiter side, there's more depletion than expected, okay? Or that can be accounted for with the planets in their current configuration. So the second simulation that we did was to ask, is this the signature of the planets migrating? Okay, so there are asteroids that are missing that we would expect to be there if the planets remained, have always been in the orbits that we find them. And so this is the result of that simulation. The bottom histogram that you see is what we find in the second simulation, where we allow Jupiter to migrate inward by that half an astronomical unit that we estimated before. And Neptune is migrating outward by I think in the simulation, we did something like 7 astronomical units. And the other planets are doing their thing as expected from the other simulations that we have. So now we are looking at the effect of those migrations of the planets on the asteroid belt. And the bottom histogram is what we produce in the simulation. The upper histogram is the actual observed asteroid belt. And if we compare those, we see that this is a much better match than we had before, with the planets not migrating. Okay, so we concluded from this that the asteroid belt as we see it needs to have something more than the planets in their current configuration. And what we actually see is consistent with Jupiter migrating inward. And so the deficit of the asteroids that we saw in that simulation where the planets do not migrate is possibly consistent with Jupiter having migrated inward by the amount we estimated. And the other thing we learned from these simulations was that the migration timescale should not have been too long, should have been only a few million years. And the reason for that is that a very slow migration actually wipes out the asteroid belt completely. What happens is very interesting. This resonance that I told you about, this MOU-II, this very subtle resonance, not having to do with the orbital periods, but rather the precession period of Saturn, the one at the inner edge of the asteroid belt, that resonance, its location is very sensitive to where the planets are, to their orbital, where their orbits are. And during the migration, the location of that resonance sweeps all the way through the entire asteroid belt. And it kicks out asteroids very efficiently. So if it sweeps very, very slowly, it's very efficient at just completely wiping out and clearing out the asteroid belt. Whereas if it sweeps fast enough, then it allows some asteroids to remain, to survive. And so we figured out that this migration should have happened over a relatively quick timescale of a few million years, as opposed to tens or hundreds of millions of years. Okay, so where are these missing asteroids? So if this migration happened while the asteroid belt was already in place, then those asteroids were thrown out. Where did they go? Some of them, well, a lot of them, the biggest target for asteroids when they're being ejected or scattered, the biggest target is actually the sun. They fall into the sun. So we actually looked at how the sun's atmosphere might have been contaminated. It's too difficult over gigayears. It's too difficult to actually preserve any signatures of that kind of contamination of the solar atmosphere. So the thing that then we looked at was these asteroids, as they were being scattered, would also have impacted the planets, the rocky planets. And is there evidence in the impact crater record of the planets and the moon? So it turns out, astonishingly enough, there is. That the impact craters on the planets, so these are, you see the surfaces of Mercury, Venus, Mars, and the moon. Earth itself is not so useful because Earth is geologically active, and its ancient impact craters have been mostly wiped out. Occasionally you'll hear in the news that we've discovered or identified ancient craters on the Earth, but they're very few and far between. On the other hand, these planets, Mercury, Mars, and the moon do not have atmospheres, and they have preserved craters from about 4 gigayears ago. Mars actually has been active geologically early on, and Mars turns out to be a very interesting case where it has preserved craters at because it has geology and geological activity in different phases over its history. We actually get snapshots of the impact craters at different periods in over gigayear timescales. So Mars is a very interesting case that way. The moon has preserved craters throughout its history. It's not been geologically active since about at least something like 3.5 gigayears. Okay, so it turns out if you look at the craters on these planets, there are actually two different types of craters. And what you see here is crater diameter on the horizontal axis, and on the vertical axis is a measure of crater density. So on the lower curves, the crater density is low, and the higher ones, the crater density is high. So if you look at parts of the moon, look at sections of the surface of the moon where there's high crater density versus low crater density. And actually the measure on the vertical axis is not just the crater density, it's actually deviations from a power law of index 3. So there are, of course, more small craters than large craters, and that power law, and it's a power law size distribution, approximately a power law of 3, but there are deviations from that index, that power law index. And this is the astonishing thing, that the parts of the moon and Mars and Mercury that have low crater density have almost exactly a power law of 3, which appears as a flat curve on this because we're looking at deviations from a power law of 3. Whereas the high crater density units on the moon and Mars have this shape that you see, this humped shape, and it's quite distinct from the low crater density regions. You can actually see that if you just take a telescope, take a look at the moon with even a pair of binoculars on a full moon night, you can see that there are high density. There are parts of the moon that have very high densities of craters and parts that have low densities. The high densities are bright to the eye. You can see that they reflect a lot more light, and the lower density regions are what are called the lunar mare, and those are where there have been lava flows more recently, and so the older craters have been wiped out, and so the darker regions are younger, geologically younger, because the older craters have been wiped out, and so there are fewer craters, and so they've accumulated, so over time they've accumulated fewer craters. So we call these population 1 and population 2, kind of like stellar populations. Those of you who might be familiar with stellar dynamics. So population 1 is the older population with high density craters, and population 2 is the younger population of craters with a lower density of craters. So then what we can do is look at those size distributions and ask what were the sizes of the projectiles that made those craters. And there's a relatively simple scaling law between the size of a crater and the size of a projectile. And just not to clutter things, I'm showing here only two cases. One is the lower one is the data we have from Mars for the young craters, the craters, the low crater density regions on Mars. And the upper one is from the lunar highlands, where there are lots of craters, high density craters. And we converted those to projectiles. So what are the sizes of the projectiles now, rather than the craters? And you can see that the shapes are slightly different. So the lower curve, for example, isn't exactly flat, and that's because of the scaling law, but they're quite distinct from each other. So the projectiles that produce those two different types of craters had a different size distribution themselves. The projectiles themselves were of different size distributions. We call them population 1, population 2. Population 2 has an asymptotic power law distribution, which has an index of 2.5. The population 1 at small sizes, small crater sizes around by small here we mean kilometers in diameter, has a power law index of 2. So it's quite distinct from that the power law of 3, which is the average power law of craters on the moon. So then what we did was we compared this to the known populations of small bodies. So what we have is, so these red dots are what I just showed you in the previous slide. These are the sizes of the projectiles that we inferred from the craters. And on top of that, I'm showing, I've plotted the sizes of asteroids that we find in the asteroid belt. That's the upper one, the blue and green ones on the top. We find that that the asteroid belt, in the main asteroid belt, falls right on top of the projectile sizes that we infer for the ancient craters on the moon. The younger craters, on the other hand, are very closely, a very close match to the size distribution of the near-Earth asteroid population. Okay, so the near-Earth asteroid population is this transient population, which is unstable. It lasts for a few million years, and then it's resupplied. It's resupplied from the asteroid belt. That's our current understanding. So the near-Earth asteroid population is different in sizes and different in size distribution than its source population. And the reason for that is quite subtle. Why, the near-Earth asteroids come from the asteroid belt, they're resupplied continuously from the main asteroid belt, but they're not a reflection of the size distribution of the asteroid belt. And what it is that the near-Earth asteroids are overabundant in smaller asteroids compared to the parent population in the asteroid belt. MBAs are main asteroid belt. So the NEAs are derived by a size-dependent process from the main asteroid belt. Radiation forces, I mentioned this already before. Radiation forces make the smaller asteroids more mobile, and the small asteroids eventually drift into these Kirkwood gap regions, where they are then perturbed into planet crossing orbits. So in the Kirkwood gaps, the orbits become chaotic. Their orbital eccentricities get pumped up until their perihelion distances enter the region where they can intersect with Mars, Earth, and all the inner planets. So the smaller asteroids are more affected by the solar radiation effects, and that's why the near-Earth asteroids are more abundant in the smaller asteroids, and so their size distribution is distinctly different. Okay, we can actually, and this is all consistent with the physics that we expect, the difference in the size distributions. So what does it mean that population 1 craters are consistent with projectiles from the main asteroid belt? Okay, so, well, one can say, well, that means that the projectiles for population 1 craters, the ancient craters, came from the asteroids in the main asteroid belt without this size filter, without the radiation forces doing anything. That it almost looks like one can interpret it as if the asteroid belt were just thrown at the terrestrial planets without regard for size. And that is what we would expect from this resonance sweeping effect, the simulation that I showed you. When Jupiter migrates, its resonances, or those Kirkwood gap regions, sweep through the asteroid belt and launches asteroids. So those asteroids get launched out of the asteroid belt in a size-independent way, because that migration doesn't distinguish between small, or the effects of Jupiter don't distinguish between smaller and larger asteroids. Only the radiation forces do. Moreover, direct age dating and isotope analyses of lunar samples have shown us that there was an impact cratering spike at 3.9 gigayears. This was one of the deepest and most important scientific results that came out of the Apollo program in the 60s and 70s, that the Apollo astronauts brought back samples of the moon that were then studied in laboratories, and the radiometric dating of those samples led to this conclusion, this astonishing conclusion, that the impact craters on the moon, or the whole surface of the moon, had been reset at 3.9 gigayears, about 600 million years after the crust of the moon solidified. So both those results came out of analysis of the lunar samples. that the lunar crust had solidified at about 4.5 gigayears ago, but that it was reset. All the isotope systems, the radiometric, like the uranium, thorium isotopes, lead isotopes that come out, that are the byproducts, the end products of radioactive decay of uranium and thorium, they were in such a ratio that it showed that they had been reset at 3.9 gigayears. And the interpretation was that there was this so-called lunar cataclysm, that the moon was bombarded ferociously at 4 billion years, at 3.9 billion years ago, about 600 million years after the crust, the lunar crust had already solidified. Okay, so from that we made this link that so this was the first explanation or a link to dynamics, to the dynamical evolution of the solar system, that there was this rearrangement of the planetary orbits, that happened at 3.9 gigayears ago and produced this heavy bombardment. So why was it 600 million years after the birth of the solar system? So here's this one scenario that was proposed some 15 years ago now. I think am I out of time now?
You could maybe take a couple of minutes more, if that'd be okay. Maybe about maybe even 5 minutes is okay, if that's all right. If we could.
Okay. Yeah, sure. Okay. So one scenario is that initially the migration was very slow, but then Jupiter and Saturn encountered their own. They hit a 1 to 2 resonance between their orbits, and that led to a lot of chaos in the solar system. When the planets themselves hit a resonance, an orbital resonance, they can perturb a lot of things in the solar system when these giant planets do that. And here's a simulation of that. It's known as the NEAS model. It's gotten a lot of press coverage, and it's very popular. So the idea there is that Jupiter and Saturn hit this resonance as they were migrating, and they caused a very quick perturbation to the solar system, and that happened, that was triggered at 600 million years. So you see that in the simulation, something awful happens, like Uranus and Neptune switch places because of this perturbation. So this has been studied in many simulations now in the last 15 years. It's great. It provides a natural trigger for this late instability of the solar system. However, sadly, it turns out that it's incompatible with many properties in the Kuiper belt. And I won't go into the details of that. It's also incompatible with the stable orbit of the Earth. Okay, we know that the Earth's orbit has been more or less where it is. We don't have great constraints, but we know that, say, the moon, for example, the moon is as old as 4.5 billion years, and it was bombarded at this 3.9 gigayears ago. But if the giant planets did what this NEAS model says, that we shouldn't be here, okay, Earth should not be here. So this is no longer a possibility. Another possibility is that Uranus and Neptune took a longer time to form than Jupiter and Saturn, and they took something like 600 million years beyond the other planets to form. They formed slowly, and this is has been talked about for a long time, that Uranus and Neptune took on the order of a gigayear to form. But then there has been some suggestions of how to make that more efficient. So the story of Uranus and Neptune formation still remains incomplete. But Uranus and Neptune are really key to the migration. If they don't exist, if they took a long time to form, then there's no migration. The planets, the planetesimals are not getting cleared from the outer solar system until Uranus and Neptune come on the scene. And so so a slower formation of Uranus and Neptune could solve this problem. But there are other issues with Uranus and Neptune. If they take very long to form, then astrophysically, we don't expect them to have the giant hydrogen atmospheres that they do have. So there are unsolved issues with that. Yet another possibility is that there used to be a fifth giant planet roaming in the outer solar system, that its orbit became unstable about 4 gigayears ago, triggering the migration. And so the debate and the research continues on this. So I'll summarize now that, so your takeaway points are that the solar system has not always looked like it does now. The orbits of the giant planets were more compact. There was a lot more debris 4.5 gigayears ago. And we think that there's good evidence that about 4 gigayears ago, this debris cleared up and the planets settled into their present orbits. That dynamic period had consequences on the inner solar system. There was this heavy meteoroidal bombardment at 3.9 gigayears ago. And subsequent to that, there are only traces of the asteroids and comets left in the solar system. And hence, ever since then, we have low bombardment rates by meteoroids, large meteorites, particularly on Earth, which is a good thing, which has allowed us to be around now. The evidence is in the Kuiper belt, it's in the asteroid belt, it's in the impact craters on the terrestrial planets, it's in the meteorites that we measure in our laboratories, and the details are under active study and debate. We don't have all the answers. And I'll leave you with these big mysteries to connect with your lecture series, the mysteries of the universe. The big mysteries in the solar system are how to account for the differences between Jupiter and Saturn. These are giant gaseous planets, whereas Uranus and Neptune have much smaller gaseous envelopes. Is the solar system architecture uncommon? Is it fragile? Everything I've learned over my career is that the solar system is really very delicately arranged for us to be around. And then finally, what is the effect of giant planet migration on the inner planets' orbits? This is an issue that we still have. We have all this evidence that the planets migrated, but we haven't quite figured out how the inner planets' orbits came to be. And I'll end over there, and I'm happy to take questions.
Okay, thank you. Thanks a lot for that beautiful tour into a planetary migration. So let's have a round of applause for Professor Malhotra's beautiful lecture, and then we move on to the questions. Okay. So is it okay if we start with the questions? There are actually quite a few of them.
Okay, yeah, sure.
Okay, great. Let's see. So, okay. So the first is, in fact, it seems to be a comment, in fact, one of the mysteries that you already pointed out, but I'll just read out the question because that's the first question. So the planets that we know, this is a question from Vanchaj Kerni, which is planets that we know today, formed near the stars, that is the sun, result in solid surfaces, while Neptune consists of gases. Why is it so? I think that's roughly the question.
Sure. So the overall chemical differences between the inner planets and the outer planets has to do with there was a temperature gradient in the disk out of which the planets formed, the astrophysical, what's known as the protoplanetary disk, out of which the planets formed. And in the inner part of the disk, early on, only the solid materials could condense, or what are known as the non-volatile elements and minerals could condense. The temperature was too high, so the gaseous, the gases could not, or the volatile elements, in particular, say H2O, the water molecule, which is very abundant in protoplanetary disks, could not condense in the inner parts of the protoplanetary disk. Only in the outer parts it could condense. And because it's the most abundant molecule, you get large planets when H2O condenses, makes solid planetary cores. You get large planetary cores. In the inner planet, you simply wouldn't have H2O condensing. The solid materials are, the metallic elements and minerals would condense, but they're very small in abundance in protoplanetary disks. So we would get small rocky planets close to the star, and giant gaseous planets, once the H2O molecules and other ices condense, which are in higher abundance, they can then attract gases, the hydrogen and helium, which is of course the biggest in abundance in a protoplanetary disk. Those could condense around the planetary cores that formed out of H2O, condensed H2O, and other icy materials. I hope that answers the question.
Great. Vanshul had another question, which is, when did Neptune migration take place? Around what time?
So the best estimate we have is about 3.9 gigayears.
Okay. So there's a question by Rohit. It says, I read somewhere that due to conservation of angular momentum, all planets have their orbits in the same plane, but Pluto's orbit is 15 to 17 degrees tilted. So is its orbit coming in the same plane as the other planets? Or does it lie in the same plane as the other planets?
Right. So Pluto's orbit does not lie in the same plane as the other planets. And as I walked you through that, we think the best explanation we have is that it was captured in this resonance with Neptune. And as it migrated along with Neptune in this resonance, its eccentricity, its orbit got more and more elliptical, and it also got kicked out of the plane of the planets because of this resonance.
All right. There's a question by Bebhav, and if I understand correctly, it says, most exoplanets being hot Jupiters, were very close to their stars. Can one use a similar model used for Neptune here to predict that with time, these hot Jupiters would migrate outwards?
So the hot Jupiters, so this is, I work in that field too. The hot Jupiters, it turns out, were, they looked like they were very common because initially those were the ones that were found, but that was due to observational bias because of the technology that we use to detect planets. So nowadays, our estimate is that hot Jupiters are actually rather rare. There are only about 1% of stars have hot Jupiters. And our current understanding is that these are systems where the protoplanetary disk was very massive, had a lot of very high density gas. And in that gas, the Jupiter mass, a planet forms very quickly, almost like a star, and it migrates inward actually. It migrates inward in that gaseous disk. So it forms at larger distances, but migrates inward because of the interaction with the gaseous disk. So basically friction with the gaseous disk causes this Jupiter mass, or actually typically they're, right. So these Jupiter mass planets actually migrate inward, and then they stop at some radius, which is typically on the order of 10 times the stellar radius. And that's because of other magnetic and other interactions near the star, which reverse or stop the inward migration. And you asked about how this might relate to Neptune. We don't think that it has any relationship to Neptune.
Okay, so there's a question by Marashli, and the question is, what is the time scale of back reaction migration?
I'm sorry, could you repeat that?
It says, what is the time scale of back reaction migration, planetary migration?
Of migration? Yeah, so we think that it's on the order of something like 10 million years.
I see. Okay, as a question by Deepan, it says, isn't there any migration of planets like Saturn or Uranus? And if so, does the migration of these planets bring about any discrepancy in the calculation of Jupiter's migration?
So yes, there is migration of Saturn and Uranus. And we know that only from the numerical simulations that have been done. We don't have any straightforward link to anything that's observable now. The straightforward links to observations are to Jupiter's migration and to Neptune's migration. There's a little bit of a connection between Saturn's migration and the inner edge of the asteroid belt. So there's still room to do some research on that. We don't have clear answers on that yet.
All right. There's a question by Parth. It says, assuming that Neptune really shifted by some amount mentioned in your lecture, what do you think would have happened to Neptune's moons? Would they get ejected, or would they collide with Neptune or something else?
So Neptune's moons just adiabatically move along with Neptune, the inner moons. The outer moons are thought to be captured, and they could have been captured at times that very late times, having very far removed from the time of migration. So most likely that would be the case, or they might have been during that time. So we don't have a handle on a time scale for when those moons were captured. The inner moons of Neptune would, however, just simply adiabatically move along with Neptune with no effect from due to the migration.
Okay. There's a question by Devesh. It says, as planetary migration should be happening in other stellar systems as well, how does this affect our search for exoplanets? And also, can there be any other reasons for planetary migration?
So planets, I mentioned that with hot Jupiters, we think there's migration because of the interaction with the protoplanetary gaseous disk. The migration that I described for most of my lecture had to do with the interactions with the planetesimal disk, and that's the late stage, very late stage. After the planets have formed, the gaseous disk is long dispersed. So with exoplanets, what we see is the current state. So it's far after the formation stages. Can we link it to planet migration? Now, recently we are able to actually peer into the protoplanetary disk stage when the planets are forming. And the observations are still, the technology is still not quite good enough to see the planets that are embedded in the gaseous disk, but it's getting there. Now the time scale for the migration is longer than human time scales, much longer. But there are possible links to actually current observations and the migration in the gaseous disk. We can see structures of if there's a planet that has formed and is interacting with the gaseous disk, there are structures like spiral arms that the planets launch, and those are just about becoming possible to observe.
Okay, there's a sweet little question by Sagnik. It says, if Neptune is migrated from its orbit, then why is it considered to be a planet and Pluto is rejected as a planet?
I don't think the definition of planet takes into account whether the planet has migrated or not. The definition adopted by the International Astronomical Unit has more to do with the sizes of the planets and their masses, and also what else is in the neighborhood of the planet. So Neptune is a big enough planet, and its neighborhood is relatively cleared of small bodies. Pluto, on the other hand, is embedded in the Kuiper belt, which is lots of small bodies. So Neptune is a bona fide planet in that definition. The definition doesn't involve migration.
All right, great. And so there's a question by Oregunta, and the question is, as we know that Jupiter is surrounded by large asteroids, is there any possibility to avoid these asteroids by our current tech from Earth? As NASA has been saying, so many might happen in the near future, like Oumuamua, but it didn't happen. So how can we minimize the error in detection of these asteroids?
Of the asteroids near Jupiter, is that the question?
I believe so, yes.
So yes, so Jupiter has asteroids in its own orbit. They're called the Trojan asteroids, the Trojans and Greeks actually. There are two clouds of asteroids that orbit approximately 60 degrees ahead of Jupiter in its orbit and 60 degrees behind. Those have been detected, and there are astronomical observations that continue to monitor those. So I'm not sure what was beyond that question.
I'll probably read it out
Minimizing
again.
what?
I would read it out again, the second part. As NASA has been saying, so many might happen in the near future, like Oumuamua, but it didn't happen. So how can we minimize the error in detection of these asteroids? That clarifies the question.
Okay, that question, yeah, it's not, that question is not speaking to me.
Okay, all right. We have others. Maybe the concerned person could put a clarifying remark as a follow-up, and maybe we could see if we could take it up later.
Okay.
So there's a question by another one by Marashli Muhammad Ali, and it says, how do we find craters age from their images?
Oh, okay. No, we don't find ages from their images. What we do find is, well, okay, in an indirect way we do. We get relative ages because the images tell us the density of craters on a particular surface. The higher the density, the older the surface, because it's been accumulating more craters over time. So we can get relative ages from images. The absolute ages we get from the samples, the actual samples of rocks that we get from those bodies. So the direct ages that we have are mainly for lunar craters. So we have samples of the moon, and we have studied those in the laboratory. And in the lab is where we measure the actual ages. The images tell us relative ages.
Okay, there's a question by Bidisha, and it says, what are lunar highland projectiles?
Oh, so the lunar highlands are parts of the surface of the moon that have a very high density of craters. They're also literally at a higher elevation compared to the average geoid shape of the moon. When I wrote down projectiles, what I meant was that if you look at a crater on the lunar highlands, you can estimate what is the size of the projectile that made that crater. So that's what that meant. Projectiles that hit the moon and created a crater. So the size of the projectile as it is related to the crater.
Okay, there is another question by Oranguta, and the question is, why do we observe so many hot Jupiters unfathomably close to their star, as without another large body's influence, should it not eventually be swallowed up?
So hot Jupiters are more easily observable because of our technology. It's like because the bigger the planet, so Jupiter mass or more, and the closer it is to the star, the bigger the wobble that it creates on the star. The way we actually detect the hot Jupiter is because it causes the star itself to wobble around the common barycenter. And so that's why we see hot Jupiters more easily than we see Jupiters that are farther away. And then I guess part of the question was, is there an influence of another body? And the answer to that is our understanding is that these hot Jupiters got to be hot Jupiters not because that's where they formed farther out, but they migrated inward by friction in the protoplanetary disk. So in that sense, the other body that you're thinking of is the protoplanetary disk. There was influence of such a body to make a hot Jupiter.
Fine.
And why do they not get swallowed up by the star?
Yeah.
Okay, right. So that question is not so easy to answer, but there are some rough understanding of that is once a Jupiter mass planet gets close enough to the star itself has a very strong magnetic field, and it creates a cavity near the star. So there's no more protoplanetary disk at some close distance to the star, and then the hot Jupiter stops there. So it doesn't get all the way into the star. But it's also possible that stars that don't have or have other dynamics of their magnetic fields do swallow up hot Jupiters. And of course, we wouldn't know because they're already gone into the star.
Right. So now there's a question by Deepan again. It says, would asteroids entering into the Kirkwood gaps and then impacting celestial bodies change the inclinations of the impacted bodies?
Well, in a tiny way, but typically the asteroids are so small compared to the planets that they don't change the planets a whole lot. If they impact other asteroids, which is also possible, asteroids do impact each other, then they do change their orbits a little bit more. They change their spinal orientations. They can even shatter asteroids, and we see evidence of that. There are so-called collisional families of asteroids in the asteroid belt, where there's a whole, you can see that what used to be a single asteroid has broken up. It has very similar orbital parameters. They're very tightly concentrated in orbital parameter space. So we can recognize the fragments of collisions in the asteroid belt.
Okay, there's a question by Shreya. Could you please further explain radiation forces and how they affect the motion of asteroids?
Okay, it's a very good question, and it's a very the physics is very beautiful and very and rather complicated, not straightforward. So radiation forces change the orbits of an asteroid in the following way. Because an asteroid, it absorbs solar radiation and it warms up to some equilibrium temperature, and it re-radiates, of course, because incoming solar radiation is equal to outgoing radiation from the asteroid. Otherwise, the asteroid would keep heating up. So there's an equilibrium. But so the asteroid re-radiates radiation, let's say uniformly, like a black body, approximately black body. It radiates at a different temperature than the sun. So the radiation from the asteroid goes out isotropically. The radiation from the sun is coming in one direction. As the asteroid rotates, the highest point or the highest temperature point on the asteroid is displaced because the asteroid is rotating. The incoming radiation from the sun is not in the same direction as the average outgoing radiation. It's a little bit like during I guess if I can be Socratic here, okay, I won't wait for an answer. So the sun is on average, on any averaged over the year, the sun is at its highest. It's up high at noon, but the hottest part of the day is around 2 p.m. And the reason for that is the Earth warms up over its rotation period over the day. And so the outgoing radiation or the equilibrium and the largest temperature occurs a little bit after the sun is overhead. And in the same way, that's the same way for asteroids. And so that slight mismatch means that the outgoing radiation produces and the incoming radiation produces a net torque on the asteroid, and that torque changes the angular momentum, the orbital angular momentum. So the asteroid's orbit will then change, and that will depend upon whether the asteroid is rotating in a prograde way or a retrograde way. And in one case, the asteroid's orbit angular momentum will increase. In the other case, it will decrease. And that's how the asteroids become mobile in their orbits.
Great. There's a question by Lai Chi Long, and it says, how does H2O in its gaseous state impact planetary formation?
In its gaseous state, okay. I can't give you a clear answer to that. I don't know that there is any clear answer to that. This is a very chemistry question, and how minerals interact at very small scales. I don't know of any any big picture effect of that.
Okay. There's a question by Vansha. It says, can migration occur in case of moons? For example, in the case of moons of giant planets, can migration take place in these systems?
Yes. So the moons of the planet, especially like the large moons, for example, Jupiter has this little miniature solar system, right? With the moons that were discovered by Galileo. They're called the Galilean moons. Io, Europa, Ganymede, and Callisto. Those are thought to have migrated, but under tidal forces. So tides are very important for moons, and Io and all these moons are actually observed. In particular, Io, I think, has been observed. Its orbit is getting bigger over time. We can actually measure that migration going on even now.
Okay, Origunta has rewritten his query, and I'll probably just read it out one last time to you. The former part was, I think, already clear, but I'll still read it out in its totality. So Jupiter is surrounded by large asteroids. So is there any possibility to avoid these asteroids from Earth using our current tech in near future? As NASA has been saying, so many might hit our Earth like the MOU-II, and I quickly Googled it. It's one of these extraterrestrial objects which were detected in 2017. So just I was curious about this term. I had never heard it myself. So anyway, so what Origunta says, as NASA has been saying, so many might hit our Earth like the MOU-II, which passed recently. So how can we minimize the error in our tech to analyze the impacts to avoid this?
So, okay, so I don't think he or she is asking about the asteroids that are near Jupiter. In general, asteroids can hit the Earth. They do hit the Earth from time to time. We see meteors. Those are tiny asteroids that are hitting the Earth. Sometimes we see meteorites that are bigger, and over longer times, we see sometimes even bigger objects that have hit the Earth. So we can't fully avoid impacts. We actually cannot avoid impacts. They do happen naturally. As far as Oumuamua is an interstellar asteroid that was discovered, that was passing through the solar system. So it came from some other stellar system, apparently, and just passed through the solar system very quickly. And we observed it over just a few months, I think. And these interstellar asteroids are thought to pass through the solar system and through the inner solar system, and even get close to the Earth from time to time. Approximately one per year or so, or one per 10 years in order of magnitude. Can we avoid impacts by those? Well, if they're really headed right for Earth, I don't know that we can do anything to avoid that. Other than perhaps if we have enough warning to send something out to change the course of that object or destroy that object. So people think about these things. Nothing has so far been needed to be put into action, but people have some ideas on what to do about these. I hope that kind of answers that question.
I hope so, yes. I guess because that was the last query from the chat session, maybe I could probably squeeze in one little query of mine, which is there's this, of course, this mention of chaos in the title, and you did mention something about dynamical chaos during a lecture. I was just curious, is it, the common sense expectation of where this would figure is that most likely this would be, for example, when you're looking at the effects of these planetesimals, a beautiful term that I learned from you today, their effects on these planetary trajectories as small gravitational perturbations. If a tiny change in the perturbation would change the trajectory completely. So maybe is that the sense in which the term chaos is being used, and in a quick follow-up on that is can that be kind of explained by incorporating effects of general relativity into the calculation, like one usually does? Let's say the simple things like bending of light around gravitational masses.
Okay, so you had a whole bunch of questions in there. So dynamical chaos, I mentioned that in a very big picture way. Yes, these small bodies affect the orbits of the planets, and that's part of the dynamical chaos. I would say in a big picture way, the way I meant it in the title was that the solar system was unstable in its in its young age. And that's what caused, so all of this migration was a consequence of that dynamical chaos and instability caused by this interaction between the small bodies and the planets. In a more focused way, dynamical chaos is everywhere in the solar system. When I described to you these orbital resonances in the Kuiper belt, and for example, even Pluto's orbital resonance with Neptune, dynamical chaos figures there. Okay, the phase space around these resonances has parts that are chaotic and parts that are quasi-periodic. These Kirkwood gaps in the asteroid belt that are resonances with Jupiter, the reason that they are empty, and I mentioned that this is a long story, one could spend a couple hours talking about that, that has very, very rich dynamical chaos features. You know, there's this sensitivity to small perturbations. There's or extreme sensitivity. The phase space is chaotic. There are multiple dimensions of phase space. One can look at simplified models and more complex models. So there's very rich dynamical chaos in everything associated with anything to do with orbital resonances. And everything that's non-trivial dynamics in the solar system happens because of this chaotic resonance dynamics. So there's a huge literature on that if you're interested. There's a whole field of dynamical chaos and planetary dynamics.
Okay, very good. Okay, I think we should thank Professor Malhotra once again for her incredible patience with so many queries, and of course, in addition to her wonderful talk. So thank you so much, and we're very grateful to you for accepting our kind invitation. And I thank everybody in these difficult times for attending this lecture today. And thanks again to the beautiful team of what I call as a Packers of Physics and Astronomy Club of IIT Roorkee and the Roorkee Chapter of the Indian Physics Association, who provide us with their invaluable tech support for duds like me. So thank you so much, Professor Malhotra. I wish you a good day. Please stay safe. Thanks once again. Thank you.
Thank you, and everyone, take care. Make good choices wherever you are, and keep yourself and others safe around you. All the best.
Thank you.
Okay, bye-bye.
All right, team. So thanks once again. Thanks, everybody. And tune in one last time this Saturday for the conclusion of this MOU ILS-II this year. So till then, please stay safe. And this is Alok signing out.